Thank you for the light. Sibuk dekat kamera. Go, Hakim.
Yeah, Mat. What's going on?
Just now I created a TikTok account.
Yeah.
And then Dr. Ang entered my live TikTok.
Yo, serious lah?
Yes, and then he asked about the assignment. So I wonder, have you finished the assignment?
Yeah, sure. I can say it to you if you want.
Yes, that's what I like.
Yeah.
Yeah, okay.
What is What are you doing?
I'm just bringing up here.
Oh,
So, where is it?
he's going to Osman.
Oh, I see.
You know about or something?
What is it?
There's rumor that everyone started to spread that they say that Dr. Ang got a TikTok account.
Yes. Wow,
So,
that's crazy.
you guys need to be careful. If something happens.
Actually, let me tell my friends about it.
Okay, I'm going now.
Thanks.
See you.
Right.
Hello everyone and welcome to our presentation on the real-world application of first ordinary differential equations. When we think of engineering mathematics, our mind usually drifts toward mechanical systems, electrical circuits or heat transfer. However, the exact same mathematical tools we use to track physical changes can also be applied to human behavior and social dynamics. For our group project, we decided to explore a unique and creative application of the first ODE, which is the mathematical modeling of how a rumor spreads through a population. To give our project a concrete scenario, we are simulating a classic mystery theme inspired by Detective Conan, looking at how fast the rumor of a student's sudden disappearance spreads through a closed school campus. While this sounds like a plot from an anime, tracking the velocity of information is a highly serious concept in modern data science, identical to how tech companies predict viral social media trends. At the absolute core of this application is the concept of a rate of change, which we write mathematically as dy over dt. In our model, y represents the number of students who have heard the rumor at any given time t. The speed at which the gossip travels does not just happen at random. Instead, it is directly proportional to two factors working together: the number of people who already know the secret and are actively spreading it, multiplied by the number of people who are still completely in the dark. This behavior is perfectly captured by the logistic growth equation, which takes the form dy over dt equals to ky open bracket n minus y close bracket. In this differential equation, n represents the total population of the school, which acts as our limit or carrying capacity, while k is a constant that represents our specific transmission of gossip rate. Because this equation contains the unknown function y and its first derivative without any higher derivative, it is classified as a first ordinary differential equation. More specifically, it is a non-linear separable ODE, meaning we can solve it completely by separating all the y variables to one side, moving the time variables to the other, and integrating both sides. When you plot the solution to this equation, it creates a very distinct, smooth S-shaped curve. The rumor always starts out incredibly slow, and when only a few individuals know the secret, then it explodes exponentially in the middle as it goes viral across the campus. And finally, it levels off to zero as almost the entire population fills up and runs out of new people to tell. Now that we have established the mathematical foundation and the variables of our rumor mystery, I'm going to pass the floor over to my teammate who will walk you through our specific problem statement and a step-by-step algebraic solution.
Imagine a rumor starts at an university through WhatsApp group among friends. So at the very beginning, only few students know about the rumor. But as time goes on, the spreading rate will be very high. So we can model a mathematical solution using the first order differential equation it will be the linear first order differential equation. So for example, if we take that p of t is number of students who know about the rumor and n is the total number at the university. So n minus p will be the number of students who have not heard about the rumor. So for our model, the rate at which the Rumour spreads, which is dp over dt, is proportional to n minus p, which means the newer students. So the proportional dp over dt is proportional to the newer students. So if we assume that at the initial phase our n is equal to 1000, which means the total students is 1000 and p is only 50, so n minus p is definitely 950 if we subtract it from the p. So the rate will be very high because 950 is a huge number compared to the 50. So dp over dt, which is definitely the rate at which the Rumour spreads. So it means the more unaware students means the faster spreading. So for the mathematical model, we can just pull out the proportionality constant and we can place like the k, which is a constant of spreading, which is a constant for spreading, and k is definitely greater than 0. It represents how fast the Rumour spreads. So by using that example, we can definitely understand it now. So for the graph, at the very beginning, only 50 students know that is shown in the graph. So the graph is increasing gradually at a very high rate. Slowly it decreases when almost all of the students know the Rumour, and it starts to decrease even even at a higher speed. So when all of the students know, the graph is linear and it stops there. So this is our graph for this equation.
So to conclude that this project shows that the first order differential equation can model social behavior such as rumor spreading. Mathematics help predict how information spread in communities and social media networks. By using first order differential equation, we can turn a vague concept like hype or gossip into a quantifiable curve, allowing us to predict not just if a rumor will spread, but exactly when it will reach its peak. A rumor also doesn't just stop spreading because it gets old, but it stops spreading because the network runs out of fresh mind to infect. First order differential equation gives us the exact mathematical map to see when, where, and how fast the saturation point will hit this line. So I think that's all from us. Thank you.